So you're anxious to see how we're going to use the electric potential, aren't you? Let's take a look at this situation. We have a charge distribution that's filling the space around it with an electric field. We want to move a particle from A to B in that electric field. And our particle has some charge on it. Let's say it has charge Q naught. We're going to move it from A to B, and we want to know how much work does our field do moving that charge over. If our charge is positive, the field will push it from A to B, doing positive work on it. And let's say that the work is equal to W naught, the amount of work done moving a particle of charge Q naught between A and B is equal to W naught. Now I want to move a different particle from A to B. I want to move one that has twice as much charge. So if I change my charge on my object from Q naught to 2Q naught, how much work does the field do in moving that charge from A to B? Hopefully you said twice as much, right? Because the distance is the same, but the force is now twice as big. F equals QE. So it does twice as much work. Now I change my mind again. I want to move an object that has 3 times as much charge. 3 Q naught is the charge of my object, and I'm moving it from A to B, and I want to know how much work does the field do pushing that charged object from A to B, and it's going to do 3 times as much work as moving the single charge, Q naught. And I could keep going. 4 Q naught. How much work is the field going to do? 4 times as much. Because the charge is 4 times as much, the force is 4 times as much, and the work is 4 times as much. And we could keep going. Are you getting tired of this yet? What if it was 10Q? Then it would be 10 times the work. Now, there are situations where the charge is changing constantly, and we don't want to have to go through this calculation every time. We want to come up with something that depends on my points A and B and the field that they're in, and not on the charge that I'm moving. What do? We divide the work done by the charge that we're moving between those 2 points. What do we get? We get work over charge for the first case. In the second case, we're dividing twice as much work by twice as much charge, and we get the same thing, W naught over Q naught. In the third case, and so on, we get the same thing every time, because it does not depend on the charge we're moving between A and B, which is changing because I can't make up my mind how much charge I want to move. It depends on the field that exists between points A and B only. What do we call this special value, work divided by the charge that we're moving? We call that the potential, or the electric potential. Both of those names are fine, and we use a capital V as our symbol. The electric potential that exists between points A and B depends only on the field that exists between those 2 points, and it does not depend on the charge that we're moving between the 2 points. Let's work through a little example. We have a particle with a certain mass and some charge, and we release it from rest at point A. Later, it's seen to pass point B. First question is, what is the sign of the charge of our particle? I'm hoping you all said positive, because there's a positive charge next to point A, and that's going to repel our object and send it toward point B. The next question is, if the charge on the particle is 2 times 10 to the minus 6 coulombs, and its velocity at point B is measured to be 40 meters per second, find the change in kinetic energy of our particle as it moves from A to B. Change in kinetic energy is the final kinetic energy minus the initial. And we were given that the initial velocity was 0. So we just have to find the change in kinetic energy using the velocities and the mass that was given. I got 2.4 times 10 to the minus 5 joules. The next thing we want to know is how much work did the electric field that our particle is moving through, how much work did that field do on our particle? Work is equal to the change in kinetic energy. We just found the change in kinetic energy, so that's how much work was done on our particle. Now we want to know the electric potential difference between points A and B. See if you can figure that out from what we've done so far. So the change in electric potential between those 2 points is just equal to the work done moving our charge divided by the charge that we moved between the 2 points. And for now, I'm just going to put absolute values on this, and we're going to figure out the sign later. Sometimes our change in potential is positive, sometimes it's negative, but let's just put absolute values, figure out the magnitude first, and then we'll talk about finding the sign. $12, and the units for electric potential, volts, capital V for volts. So the magnitude of my electric potential difference is 12 volts. One of the points, A or B, is higher by 12 volts than the other point. Now let's figure out which one is at higher potential. The thing you should remember is that the electric field always points toward lower electric potential. The electric field points toward lower electric potential. Let's put a red box around that. Maybe we should put some stars there too. Don't forget that. The electric field always points in the direction of lower electric potential. So let's look at our situation. We have a positive charge. We have point A and point B, and the positive charge is sending electric field lines out like this. So the electric field points from A to B. That means B has to be a lower electric potential than A. So the potential at B must be less than the potential at A because the electric field points that way. That means that our delta V, our change in electric potential, moving the particle right from A to B, is the potential at B minus the potential at A. Final minus initial. Delta V is always final minus initial. Delta kinetic energy is final kinetic energy minus initial. Anytime you see a delta, it's final minus initial. Our potential at B is less than that of A, which means that this has to be negative. So if we're trying to find the potential difference between points A and B as we move from A to B, we would get our delta V would be negative 12 volts. So there are all kinds, you can try to memorize an equation and get the minus sign from that, but some books use in their equation the work done by the field, and some books use the work done by an external force, and they differ by a minus sign. In fact, we used to use a textbook, all their equations, none of them had minus signs in them because it was always the work done by an external force. All of a sudden, the new edition came out, and all their equations had minus signs. They decided to use the work done by the field instead of the work done by the external force. So trying to memorize these things and all the little intricacies is difficult. Just remember the equation that gives you the magnitude and see how simple it is to think about whether it's positive or negative. Just think about the answer, make sure it makes sense, make sure you get your sign right. If we are keeping track of negative signs, the change in electric potential, delta V, is negative the work done by the field divided by the charge that we're moving within that field. That means that we can figure it out. We know what the work is, right? Work is an integral. I'm going to leave my minus 1 over q out in front. And work is the integral. And I know what the force is. This is a charged particle moving in an electric field. The force is the charge of the particle multiplied by the electric field it's moving through. So my change in potential becomes negative the integral of E dot ds. We will use that a lot. If we have a constant electric field and we're moving from A to B, our integral simplifies quite a bit. Now, the first thing I'm going to do is take the magnitude of both sides. I'm not going to worry about my dot products and minus signs and all that stuff. I'm just going to find the absolute value of my potential difference, and then I'll look to see if it has to be negative or positive. It's a very straightforward procedure. Because our path is along the electric field, the dot product is going to give us a cosine of 0 degrees. And this just becomes the electric field times ds times 1. The electric field is constant, so it comes out of the integral. And the integral of my path length is just the total distance between those 2 points. I'm calling it d. So the absolute value of my potential difference is E times d. In this case, if we're going from A to B in the direction of the electric field, does it have to be positive or negative? Our final potential, VB, is less than our initial potential, VA, because the electric field points from A to B. It always points toward lower electric potential. This must be negative. So our delta V is going to be negative the electric field times the distance in this case, because we're moving along in the direction of the electric field, and we have a uniform or constant electric field. And if we have this situation, we're moving from point A to point B in a uniform electric field. We want to take the straight line path from A to B. But we could take any number of other paths between A and B. We can take this path. We can take this path. Or any number of other paths. It turns out they're all the same potential difference because the electric force is a conservative force. The work done moving a particle from A to B is the same on every path. And when we divide by the charge, we get the same value for each path. We can also see that if we move perpendicular to an electric field line, the electric potential can't change. So I'm going to sketch in here some lines that are perpendicular to the electric field lines. And we call those equipotential surfaces. The potential is the same everywhere on that surface because we're moving perpendicular to the electric field. The electric field points in the direction of lower potential. So if we're not moving along the electric field line, if we're moving perpendicular to it, the potential can't change. So those are called equipotential surfaces. The potential is the same everywhere on those surfaces. So moving from point A to point F to point B, the first move from A to F didn't change our potential at all. We didn't do any work moving perpendicular to the field lines. Only going from F to B did we do work and have a change in electric potential. Same is true if we took this other path. Going across this way, the field does work, but moving perpendicular to the field, no work is done, no change in electric potential. So for all three of these paths between points A and B, what's the potential difference? It's the electric field times d, the distance between those equipotential surfaces.